Yeah, the place was waiting for the to start right down the planet. All right,
let's go ahead and get started.
That'd be awesome because it's a thing.
So it is my pleasure to introduce Dr. Emily Carrington, who is visiting from Friday Harbor, Washington. Emily did her PhD at Stanford with Mark Denny on Untitled Ecomechanics, which she's done a lot of work on and we'll talk to us about today. She did a postdoc at UC with John Gosline, another big name in biomechanics, and then was at the University of Rhode Island for 9 years before moving out to University of Washington, where she's a professor and housed at the Friday Harbor Marine Lab, which is an awesome place to study invertebrates. I highly recommend it. So Emily's going to talk to us today about ecomechanics of mussel attachment in a warmer, high CO2 world.
Thank you, Kelly. It's really a pleasure to be here. I was here at Dauphin Island maybe 20 years ago. Can't remember exactly how long. So it's really great to have this opportunity to visit again and see what's new. Because I think a lot of things have probably changed in the last 20 years. Some things haven't, and Rick is still here. And the reason I'm in town is I just spent the weekend in Ocean Springs, Mississippi, and I was at the National Ocean Sciences Bowl, and I know that Dauphin Island hosted that a couple of years ago. Is that right? Yeah, so I'm a mom, and my daughter's was on the Friday Harbor team that won the Washington State Regional, so they got to go to Nationals, and they got beat by Idaho, was the actual national champions. Go figure. And I just have to say, these kids know so much about trivia, like that was just amazing how much ocean science they do know. But one of the questions they stumbled on was, what's the average temperature of the oceans? Which I'll first of all say I don't know, but their guess was 24 degrees Celsius. And I knew, my first thought was those poor kids from Idaho need to go see an ocean. I think the answer was at 4 or 5 degrees. Does anybody know what the answer is?
3.4.
3.4?
3.4.
Anyway, I digress. So I'm here and I've taken off my mom hat and putting it back on my science hat. And I'm going to tell you about ecomechanics. I'll take a little bit of time to define what I think that means. And I'm going to tell you about mussel attachment and hopefully convince you that it is a very cool thing to study, but also an ecologically important thing to study and an economically important thing to study. So mussels live in natural environments. Here's Bob Payne sitting on one of his favorite mussel beds out at Tatoosh Island. And we know a lot about how mussels structure communities from work like him. And then on the sides, I have pictures of some of our work at aquaculture farms. So on the left is a farm in Washington State. And here on the right is a picture I took at a farm in Spain, in Galicia. And what you see is a grower on the left, and these are his two sons. And one of the things I want you to keep in mind is that this is a grower, a third generation grower, and he really wants to pass on his business to his sons. And I think there are some really interesting challenges that they need to face. Okay, so first I want to say thank you to all the people that have helped me stand here and show all these data. I've been working on mussels since I was a postdoc back in the 90s, and I will be merging through about 20 years of data, and hopefully I'll end up to where we are today. So the main people I'll be talking about the work of today would be here, Gretchen Mazur, who was a master's student at University of Rhode Island. Moose O'Donnell and Laura Newcomb have worked at the University of Washington on a lot with the ocean acidification and the aquaculture work that we're doing. And Matt George is also a graduate student that has been involved with this. Okay, ecomechanics, what do I mean by that? I think since you guys know Kelly Dorgan, you know a little bit about biomechanics, and that concept there is to think about how organisms are designed from a mechanical standpoint, and we like to borrow tools from engineering and apply those into biological systems to see how things work. So I'm also an ecologist, and I like to meld those two fields. So I think of biomechanics, the heart of that is form and function, looking at a morphology, a structure or a form, and thinking about how that's used. And that to me is basic physiology. So the eco part comes in when you take that functional morphology analyses and put it back into the environment and ask, how does that affect the performance of an organism in its natural environment? And then ultimately the goal is to understand how that form or function evolves, how that affects its fitness. Okay, so again, I work on mussels. Bob Payne told us in the 70s that they're really important to, okay, it's not like that's flashing, it's confusing me. That mussels were important in structuring intertidal communities. And I've worked on Middleist edulis in Rhode Island when I was on the faculty there, so here's a nice patch of mussels in Narragansett Bay. And I've also done some work with Middleist californianus, the California mussel that's common on the outer coast, and Middleist trosselis is our local bay mussel. And I want to tell you a bit about the aquaculture industry. So mussels are very important shellfish commercially. I know I'm here in oysterland, but in cooler, temperate waters, it's all about the mussels. And the way they grow them is on lines. So they rely on mussels to attach to these ropes of some sort. They might be in these vertical ropes or hung like Christmas tree lights. But the idea is you put small larvae or seed out on these ropes, let them sit there for a couple of months or maybe up to a year. They'll start to look something like this. They'll bring them onto a harvesting barge, strip them off the rope, send them through a debissing machine to take off the beard, those threads that people don't like to eat. Put them in bags and send them off to market. So typically they have a supply and demand set up that they're going from farm to table in about 24 hours. So this is me in Spain, and one of the reasons this is the grower that you saw earlier, and the reason I was there is this right here. What he was showing me is that his crop at certain times is tumbling off the ropes, that they have really weak attachment. And this is really a problem. Both, they call this fall off or dislodgement in natural populations. It happens here on a rock in Narragansett Bay, and then these bare ropes at the aquaculture farms. And so 20 to 30% of the population can be lost annually from these fall off events. So that's not good for business. So when I came to Rhode Island, one of my goals was to see if I could use this biomechanical approach to predict when and where we would see fall-off events occur. So here is the aftermath of a big fall-off. This is a big storm that came through in Connecticut, and what you're seeing is about 3 meters high piled mussels, and this beach is extending, it's about the size of a football field. So a whole bunch of live animals chucked up onto the beach after a big storm event. They then started to rot and die and then slowly got washed back into the subtidal. But this is what I'm talking about as a major dislodgement event. And what my goal is to see if we can predict when and where these happen. So this is the ecomechanical approach, and in a nutshell, it's just simply trying to figure out when the forces are out of balance. So a mussel will become dislodged by a big wave whenever the hydrodynamic forces it experiences exceed its attachment force. So it's pretty simple physics. I first want to tell you a little bit about how mussels attach. I mentioned that this is what the aquaculture industry relies on. And what I have here is a video that's going to play back and keep looping through, and it's sped up 3 times its normal speed. And you're looking at animal pressing its foot against the slide of the glass, and it is secreting proteins into the groove of its foot, and it sits there for a little bit, and it's actually molding a fiber, takes its foot away, and leaves that behind. So the animal will do this over and over again, producing these adhesive plaques that are stuck to the hard surfaces. So a plaque would be formed right here. And then these fibers will ultimately come and connect into a stem and will be embedded into the tissue of the foot. Do that many times, and up to 200 of these fibers are collectively tethering the animal to the substrate. Okay, so as I mentioned, I'll talk about a couple of different species. I mentioned that Manilus californianus is the outer coast specialist. That really is a different type of mussel. I like to think of it as the gorilla of the intertidal. It's bigger, stronger, better built to deal with waves. But the tastier ones and the ones that are being used for aquaculture are collectively known as bay mussels. And they're in the Manilus edulis complex. So edulis is the one we have on the east coast, Trocilus on the west coast, Gala provincialis is the Mediterranean mussel. And all of that story is shifting because they're invading each other's territories. So we now have Gala on the west coast of North America. Trocilus is making its way down from Canada, down on the east coast. Okay, the other thing I wanted to mention is that DISL threads are pretty complex structures themselves. I said they're molded. And when the animal sticks its foot out, it's secreting different proteins to make a plaque, which are different than the proteins it secretes for this distal region, the part that's actually external to the animal, and entirely different ones that are in the proximal region. So it's really 3 different materials that are linked in this series. And I'll come back to that. Okay, so I told you a little bit about attachment force. We can measure that, and I'll show you that in a minute. But I want to just digress and tell you a bit about how we quantify hydrodynamic forces on animals. And I've done a lot of this, but just to keep it short and sweet, I'll say that there's 2 basic forces that animals can experience. Mussels tend to aggregate in these beds, and when they're getting the brunt of the waves coming by, then these ones in the middle will get pushed downstream, and what they see is a force called drag. And that's fairly intuitive to most people. Less intuitive is what most of these animals are seeing. They're not going to see drag. But the flow will scoot over this surface, and as it scoots over, it speeds up. It always has to do that when it goes over any structure. Whenever you have higher flow, that means you have a reduced pressure. That's Bernoulli's principle. So what that means is you've got a higher flow, low pressure area here, relatively higher pressure here. That pressure difference is what lifts the animals up off the substrate. Same principle that keeps airplanes aloft. So the wind is going higher, faster above the wing than below, and that's what keeps them up. Okay, so how do we measure this? One way is to go out to the field and you can drill a hole through a shell, stick a fishing hook in, attach that to some kind of force gauge. It can be a spring scale, it can be an electronic force gauge, whatever you want. It measures newtons. So that's how we measure attachment strength. And then the other piece, oh, I left out a slide. Let's go back here. So there's forces on mussels. What I wanted to say is I have a nice way of approximating that water velocity using wave theory. So if you know what the wave height is, that determines the velocity it creates when it crashes. Okay, so it's just using a simple wave theory model. So rather than measuring water velocities directly for this particular exercise, I was using wave heights, which is here. So to do that, you simply need some sort of wave height meter deployed near your slate. It loves to sit there for months on end, measuring how big the waves are above it. Okay, so those are the 2 inputs I needed for my model to predict whether an animal would be dislodged or not. So in blue, I have those 2 inputs that I measured in Rhode Island for 3 years, and these are the monthly mean values. So for wave height, actually I'm plotting the maximum significant wave height, the waviest day of each month. And what you can see is there is a lot of variation in wave height as storms come and storms go. But in general, in the summertime, it tends to be not so wavy. That's when we have the lowest wave heights. And in the winter months, we may see some large storm events. So here's one here, here's a couple there, here's a couple there. The next panel down is the biology. This is the attachment strength of mussels. And this is for 2 different sites. It's showing I call it tenacity. It's simply the force to remove, normalize to the size of the animal. And what I hope you can see is a very strong annual cycle where they're strong certain times of the year, get weak again, strengthen. So you see the same pattern year after year. Actually, we plot 6 years of data, and it's like clockwork. They're twice as strong in the wintertime as they are in the summer. So it's a pretty huge difference. So you put these two things together, and this is what your predictions would be. That you would predict animals would be dislodged in very discrete months of the year. And it's pretty much September and October, and maybe a little bit of November. So that's what these three peaks are. So sometimes you can see large storms come, but that's at a time when you have strong attachment. So the result is you predict no dislodgement. There's other times where you have weak attachment, but you also don't have any storms coming. And so you also would predict low dislodgement. And so you really need the two conditions to be met, low attachment and big storms, to happen at the same time. And that's when we get these catastrophic events. So that tends to happen late summer and early fall. Okay, so that's really neat predictions. Models are kind of fun, but you really do need to go out and test them, and so I did. So this is how we did it at one of our field sites in Narragansett Bay. Every 2 weeks we went and took pictures at the same spot on the shore where mussels were. And it turns out a really nice way to show that was during the snowstorm. So we had a permanent quadrat transect here, and there's 8 quadrats along that line that we came back to. And I had 5 of these spread out along the shore. So we were looking for things like this. Here's one of those quadrats. It's about the size of a sheet of paper. And this is pretty much 100% cover of mussels. And what we saw now 2 weeks later is that there are a lot of bare spots. I call this a blowout of the mussel bed. So something caused them to die. I quantified these events now for 3 years, and I had a whole bunch of undergraduates helping me with this using a random dot technique to quantify percent cover. And I figured out that it was about 500,000 dots that we had to say, yes, there's a mussel or no, there's not in this thing. So sadly, I'm going to synthesize all that into one graph. And what this is showing is, first of all, the predictions in the black bars. These are the same data that I showed you before. That was 3 years of data. I've just combined that into one and showing you the monthly peaks. So these black bars are the big peaks here, September and October. The light gray bars are my observations. And so I hope you can appreciate that they line up really nicely. We do see large dislodgement events. They happen exactly when we expected them. And importantly, I have lots of gray bars over here. I'm not seeing much dislodgement exactly when I didn't expect it. So those matching up the zeros, that nothing happened when I predicted nothing would happen, is actually a really important component of this study. So what this tells me is that my model can account for 83% of the monthly mean variation in the dislodgement of these mussels. So I think that's a pretty good model. Okay, so what that means is, yes, we know this fall off happens, and now we have an ecomechanical model that can actually predict the timing of this and the severity of these events. And so I showed you this slide before, but what I didn't tell you is to pay attention to that date. November 16th. That's at the tail end of that window of when I would expect this to happen. It's the early fall storms that matter. Storms that come later in the year, they might be really big and mean and seem really bad, but the mussels can handle it just fine. Okay, so why do I belabor that point? Why does it matter that we know the mechanism? And I want to just give you one reason why I think it matters. And here's 2 big storm events that happened in the New England area. It's actually after I had moved away. But within the same winter, we had Hurricane Sandy come in, and that was an October storm. And then just a couple of months later, there was another big storm that hit New England, and that was Winter Storm Nemo. The difference, there's a couple of things that are different about these. First of all, the timing. October, not a good time for mussels. February, not so bad. So if you, I actually don't know what the wave heights were like during this time, but my prediction would be the one that would be super damaging would be this October storm. Turns out October storms tend to be hurricanes. I think everybody in this room would have some understanding of that. And the prediction for the future is that hurricanes are going to be becoming more frequent and they're going to be more severe. So that, of course, is bad news for the Gulf of Mexico. But later in those years, the August hurricanes tend to track towards the Gulf, right? So it's later in the hurricane season that they tend to make their way up the coast. So I think the future does not look really bright for mussels in New England because there's going to be increased storm activity, exactly the kinds of storms that they're really susceptible to. So I think this is interesting to think about climate change and what the predictions are for the meteorologists. It's not just that it's going to be stormier in the future. We actually can get better information from the meteorologists. They can tell us what types of storms might be increasing. So they've said hurricanes are on the rise, but maybe not these extratropical storms, the classic nor'easters may not be such a problem. Okay, so back to why that model works so well. In part, it's because we do a decent job of measuring waves and how big waves are, but really the whole story is that mussels are like clockwork, weak every summer. So this is now 6 years of data averaged, showing you that twofold variation in reproduction strength. So I see this in Rhode Island, we see it in Canada, we see it in the United Kingdom, we see it pretty much in mussel populations all around the world. So what I have been trying to do in the last decade or so is try and understand why mussels are weak in the summertime. What is it in the water or about them that's causing that? I'm going to tell you right now, I still don't know. But I'm getting closer I think we're really knocking on the door. Okay, so this is where I go from ecomechanics to say it's actually an ecomaterial problem. It all comes down to how strongly attached those animals are to the rocks. It's all about the viscous. In the way an animal can change its individual attachment strength, there's really 3 different ways they can do it. One is that they can make more threads, and there is some variation in how many threads they produce during the year. 2, they can change how they make those threads. They can make them out of poor quality material. The glue could be bad, or the fibers themselves could be malformed. And 3, they could be making the same number and the same quality threads, but they decay faster. There could be some quality of the threads themselves, or else something in the water that attacks that collagen-like material and makes them weak. Again, I didn't mention this, but the fibers only last about 1 to 2 months, so they're constantly having to replenish them. So the decay process does that. So I have investigated all of these, and the reason why this is in black is that seems to be the main story, that the animals are making really lousy threads in the summertime. So that's why I consider this to be an eco-material problem. So I will show you how I can measure the material properties. I should maybe mention this earlier, but when you do materials testing, you can take individual fibers and clamp them in grips. So this is now a shiny golden thistle thread. I hope you can see that. Held between some pneumatic grips. And then there's a nice water bath that comes up, so I'm doing all of my testing in water. And gradually what this machine will do is pull the fiber in tension and extend it. So I'm measuring the stretchiness of those fibers and how much force it takes to cause that extension. So the bread and butter of any materials testing device is to measure force and extension. And with any material, you get an increasing slope, so it will support more force as you stretch it. What's weird about thistle threads is that they then, at a certain force, will start to just stretch out without any additional force. This is called yielding. You
can get this happening with, we don't make six-pack rings anymore, do they? Those plastic rings, you can pull them and it's really hard, but then all of a sudden it's really easy because they stretch. So Bissell threads will do that as well. Then they stiffen again and will break. So this is what a good, happy Bissell thread will do. It's pretty strong, holds a decent amount of force. It's fairly extensible, meaning it's pretty stretchy, and it yields before it breaks. So this is a little cartoon of what's happening in a Bissell thread. I mentioned that there are 3 different parts to it. So when you pull on a fiber, here's the short guy, and you're pulling on it in tension. And here's those 3 regions, right? The proximal, distal, and plaque region. It turns out all of this yield, that elongation, is only happening in this middle region, the distal region. And really what's happening is that there's proteins that are cross-linked. At this magical force, those bonds break, and the fibrils are starting to slide past each other until they catch again. And once they catch again, you start to see an increase in the force. Okay, so that's what's really happening, is things sliding past each other. And then you get to where either this region will break or the plaque itself will break. So the distal region never breaks. Its magical function is that it's able to yield and be extensible before the whole thing will break. So why does that matter? Why do you need fibers to be extensible? I said it really matters that the animal needs to be strong. It needs lots of threads to be strong. But why would it matter that something should be stretchy? Anybody have any ideas?
So, very turbulent environment, so you'll get forces at a bunch of different angles.
Okay, right. So that problem with the animal is they're getting hit from all different directions, but they are capable of putting their foot all around. They don't turn, but they can do this. So what's the other problem? Yeah, perfect. So if you tie something on your car, what's the most effective way of doing it? Or when you've not done it right, what was the problem? Tie something on the top of your car.
If you only attach it like on one end, I feel like if you would only put a bungee cord on one side of something that you'll have on your car.
So actually, why did you say bungee cord? That's what I want to know.
I actually haven't done this with my camera, but I'm surprised I haven't tried to attach something to the ceiling. But
What's so cool about bungee?
Flexibility.
Pardon me?
Yeah.
It's the flexibility, actually. So if you're going to tether yourself in lots of different directions and you've got very stiff tethers and you didn't get them perfectly in tension, then you go in one direction, that really stiff thing's going to break right away. And then all you've got is whatever you have in this direction. So by giving, you're actually recruiting more threads to help distribute that load. And you have a much stronger attachment than you would if everything was really stiff. And that's really important when all these forces are coming from different directions. So it's a bit of providing strain relief, and that's something engineers put in a lot of their designs. So mussels have figured that out. Okay, so what Gretchen Mazur did is test a lot of Bissell threads. She collected ones in Rhode Island when we knew they were strong, and she collected ones in times when we knew they were weak. And what she was able to show is in the spring, they have really strong, extensible, happy threads, just like I showed you. They're initially stiff, they yield, they stiffen up again, and they break at a pretty high force. So they're both strong and extensible. In the fall, she saw a totally different thing. She could barely get them loaded in the device. They broke at really low forces. They failed at really low extensions. When she went back and then tested what the distal region would have been like had the thing not broken first, its yield was at a lower yield, and it was poor quality as well. So pretty much everything about the threads was bad. So what we've been doing since I moved to Seattle is and Friday Harbor is try and understand what about the water or that time of year leads animals to make lousy threads.
So there's a whole bunch of things that could be going on in the summertime. It's a time when mussels typically have low condition, meaning their total body weight relative to their shell size is relatively low. They have low reproductive condition. Often these events are happening after they've spawned. The water is warm, that increases their metabolism, so that can be a problem, especially when there's low food supply at the end of the summer. The spring bloom is long gone. We have a stable thermocline, which means the blooms aren't going to happen anytime soon. They maybe have depleted all the water that's in that surface water. And we have also noticed that they have a high parasite prevalence, so that could further compromise their energetics. Okay, so we've got a long list of things that we could test. And when I started to do this, this was 10 years ago, and it became clear that there was yet another elephant in the room, and that is ocean acidification. Not such a big problem here in the Gulf of Mexico, but it is a serious concern in the Pacific Ocean, especially in the Pacific Northwest. And if you're not familiar with what ocean acidification is, I think most of you do know about the healing curve, where we are steadily increasing in atmospheric CO2. So the atmospheric air will then equilibrate with the surface water. And here's now some data. I should have mentioned this. This is from Mauna Loa in Hawaii. So all of these CO2 measurements were made initially by Charles Keeling here at a high point on the Big Island. Can't remember now what it's called. What is it called? Hawaii. It's really hard. Okay, so what you might not know is that Station Aloha, they've had a long time series there. They've been measuring, first of all, the partial pressure of PCO2 nearby, and it really tracks perfectly on average with the atmospheric CO2, as it should, because it has to equilibrate. And what has to happen when you start pumping CO2 into water is you see a decline in water pH. So I'm just putting this up here to show you that we really have the data that there is a long-term decline in pH, at least in the open oceans here. We've also been seeing this in the Pacific Northwest. So these are data from Tim Wooten and Kathy Pfister at Tatoosh. And I really started you out at Tatoosh with Bob Payne sitting on one of the mussel beds that's up here. So Wooten and Pfister are his graduate students, and we're measuring pH in a tide pool. And they saw a couple things. One is that there's huge fluctuations in pH daily, monthly, annually. Okay, and a lot of that is driven by the biology, primary production and respiration going up and down. So the same thing would happen in a seagrass bed around here. And it's also related to seasonal patterns in upwelling. The other thing they noticed is that on average they saw a steady decline over this decade at a much faster rate than they would have predicted based on our large-scale model prediction. So that was a huge cause for concern. And then third thing I wanted to mention is just a personal communication from Tim Wooten. He's noticed that mussels seem to have weaknesses. So that really motivated me to, in addition to all these other environmental factors that I was interested in, is to ask whether ocean acidification could affect mussel attachment. Okay, so to do that, we got funding from the National Science Foundation through a number of PIs and a number of different projects to build what we call the Ocean Acidification and Environmental Laboratory at Friday Harbor Labs. And it has an analytical chemistry lab on site. But for me, the most important thing were these mesocosms that we built. And you know what? They're really coolers. They're igloo coolers, but they're fancy ones and pretty tricked out. So we've got controllers here that will dose a reservoir down in here with CO2 to hit certain target pH values. And we test all the water in our analytical lab to make sure we know all the carbonate chemistry parameters. Then that water, when it's equilibrated, will then go drip into these little chambers here. Those are experimental chambers where we put our animals. So we are able to manipulate pH, temperature, and food supply. Done some of the food supply experiments, but I'm not going to talk about that today. What I'm going to tell you about are the effects of pH and temperature on the byssal thread strength that they produce. Okay, so some of this came out recently. Here's the punchline, is that mussels do lose their grip in ocean acidification, but I think they've got some other things to worry about too. But here's the pH, the low pH data. So we wanted to just take a moment to say what I really liked about our design is we had many of these reservoirs at our disposal. We had built them. But we decided not to do a ANOVA design. We wanted to do a single factor, multi-level treatments, because the point was we were trying to figure out where these threshold values were. Because if you just go in and pick high and low values, which is what many people were doing, they were trying to pick what they thought were ecologically relevant parameters. And so then they would find no pH effect. And it's really difficult to go and pick what's high and what's low unless you know what the whole biological response was. So we were really interested in pushing out to these higher levels of CO2, which is lower acidification or lower pH, to see where the break point was for these organisms. And it turns out, this is what we thought was ambient when we started our experiments. We now have more field data to say this is really where we are all the time at Friday Harbor Labs. We are in naturally acidified waters. And so what we thought were maybe kind of crazy PCO2s were not so crazy after all. Okay, so what we did find is that Mytilus trossulus, the local bay mussel, has weak attachment at low pH. And it turns out the magic threshold is about 1200 PCO2 micrograms per PCO2, or a pH below 7.6. And I'll come back to that number in a minute. I also mentioned that we were interested in temperature. And a graduate student, Laura Newcomb, has done that work. And so here's single factor experiment with temperature. What she found is a very strong decline in the strength of individual byssal threads when you get to these warm water conditions. And it looks like the break point is somewhere over 18 degrees. Okay. So, remember I told you that there's different parts of the byssal thread. Turns out that these two different factors, ocean acidification is bad, but it attacks the plaque. It turns out that the mussels are making poor quality adhesives under those conditions. And so we find that the animals are about 40% weaker when you get to a pH below 7.6. In the case of temperature, it's targeting primarily a different region, the proximal region, and in that case, they're about 60% weaker when we put them in hot water. So this is kind of cool because now we have the ability to make some predictions about what these threads would do if you combine the factors. So what do you do with multiple stressors? I know what they do with single stressors. Got a diagram up there. So what would you predict if we put them in a combination of high PCO2 and high temperature?
We might not get much acidification, the higher warmer climate.
Okay, let's just pretend. Do you mean like in nature you'd never see that?
Yeah, maybe, I'm not sure.
Well, let's just pretend you could, because I can come up with a scenario. If you warm up the water and it's increasing primary productivity, but then it goes somewhere and you've got hypoxia, the pH can be warm and a low pH can happen. Get actually any combination. But bear with me, let's just play that game. Hit them with both really bad things at once. I'm going to come back to that comment later because I really like it. So what do you predict? Because lots of people are doing multiple stressor experiments now, and they do have predictions. It's always good to have a prediction before you do the experiment.
If you just assume they're linear, it's going to be bad.
Right, so how much, what do you want to do? I gave you numbers, 60 and 40. So how do you want to add them, multiply them, divide, square root? What do you think?
Well, I think the simplest prediction is just assume they're both linear summation.
Okay, so 100%? Anybody else want to throw in
why are you assuming that they'll form the attachments at all at that high temperature and low pH? Because if the plaque is that much weaker to begin with, that's what's supposed to be anchoring them from the start, right? So how will that form at such a low pH and such a high temperature?
So I guess my answer is, in the pH condition, it doesn't form very well. They make them, but they're not good. But you just raised a really good point that I'm not showing today, but we've also measured the number of threads that they produce, and when the water gets really hot, they kind of give up. They're not happy. And so an added issue is whether they're even trying. So what I'll show you is data on the ones that they've tried to make. Okay, so we got 100%. Anybody else want to enter the lottery?
So 100% is obviously not going to be the case.
Trying to get people to be
I'll
bright.
say 60.
60
80.
and 80.
Are we doing it for the proximal and the plaque, or just?
So I'll show you a graph on what happens, what's the strength compared to like normal, how much weaker are they when you hit them with both thrusters?
Say like 75 at the top and 60 on the bottom.
Okay. Okay, so here's the answer. No, I'm gonna tell you the answer this way. So it turns out Kelly's right. I wonder if Kelly knows why she's right though.
Probably the same one, the 40 fall within the 60. So they fail with the high temperature before the.
Right, so if you're, I like to say, if you're like hanging from Empire State Building from a rope, and you've got two pests that are chewing at your rope. You've got like a tiny little gerbil, and then a really big bad beaver or something like that. So you know they're both bad, right? Because they're gonna go through your rope, and as soon as that breaks, you're dead. But which one are you worried about? The beaver, because that's going to break the thing, and it doesn't matter that like the little thing is still working at it, because that's not the main effect. So here we've got 60%, 40%. When you put those together, it's the weakest link that's going to fail. And so this guy might be weak, but that's even more weak, so they're always going to break due to that temperature effect. So the answer is 60%. So these two stressors are acting in series, so they don't multiply, they don't combine in any way. And actually what you'll see is, and this is Laura Nickham's now done this experiment, and this is the ANO design that I otherwise hate, which is these lower temperatures, the ones that aren't stressful, we do see a pH effect, because there's no problem at the temperature, so now we can see the effect of the pH. But when we dial up the temperature, then the threads break in the proximal region. There probably was a pH effect, but we can't see it. It's masked by the temperature effect. Okay. So back to the finding that we have mussels don't like a pH below 7.6 or a temperature below 18 degrees C. The question is, do they ever see that in nature? I mean, lab experiments are kind of fun, but they could be entirely irrelevant if they don't see that. And so this is where I've just started this project now working at a mussel farm. And my collaborators are Penco Shellfish. So they're on Whidbey Island. They're the #1 mussel growers in the United States. And they've been super helpful with helping us get this project started. So here's Ian Jeffers. He is the president of the company. Ian's become a really good friend. It turns out this is probably the most rewarding science that I've ever done in my life. I've always wanted to do something with aquaculture and mussel aquaculture, but I never really had the right combination of people and the right reason to do it. But everything's kind of come together and converged, and it's been super exciting. So Ian runs this company. He does have a degree in marine biology, and he will say that he didn't learn anything in college, but he's a really good scientist, I think, and he is a really good naturalist, and he really knows his system. And he really appreciates what we're doing. He always says, well, I kind of knew that, but no one would believe me. I need you, the academic scientist, to come in and collect the data and give us. So one of the things we use to do was to get these data sondes, these YSI data sondes that are measuring all these environmental parameters where the mussels are actually living. So we're measuring temperature, chlorophyll, salinity, oxygen, and pH. So this is Laura actually showing it to a group of congressional staffers at this point. So the sonde is here, and what's really special is that we've got this cable now going to a box that's receiving that data, and what Pen Cove Shellfish helped us do is, first of all, they did all the machinery to get this in place and attach it to their floating rafts, and they worked out the telemetry system, so the data is now going into the office to their computer, and it's now going live to a real-time server that's run by the Ocean Observing Network. So in the Pacific Northwest, our network is NANUS, and there is a site that you can pull up. You look at the map and you can click on Pen Cove and expand it and get real-time data. So that was really important for us when we were first deploying this, because I'm sitting, 70 miles away in Friday Harbor, and I want to know whether my data is being collected, and having it real-time, we know immediately if one of the sensors has gone down. The other reason why this is really valuable, so this is just a screenshot from one day, but the NANUS website, they have an app that you can put on your phone. So anybody can, on their iPhone, use that app and pull up that data. And what Ian has told me is that since we put the data in the water, all of the workers, he's got 80 different workers helping him out on the water, and they're really interested in what we're doing. To the point where here's some folks that their job is to sit on the harvesting barge and make sure that all the mussels going past them don't have broken shells and have the beard removed. So they just do that for 8 hours a day after day. On their break, he says he commonly sees them accessing that app because they've seen something different. They've noticed the shells seem a little thinner, the water looked a little different, and they're on there wondering, what does the data look like? So I think that tells me we've got a win, because I'm getting data I want. Ian's got his employees better engaged in what they're doing. And finally, Laura Newcomb, the graduate student, she's constantly talking to these people. She only goes twice a month, but when she gets them to take them on their boats to the particular raft that she wants to work on, she talks with them, and they talk back, and they say, Laura, we just noticed something happening over here. Or maybe she's got an idea of running an experiment. We run it past them, and they tell us whether that's feasible and makes sense or not. So our science has gotten so much better from working with the people that are actually on the water every day. Okay, so I'm going to show you just some preliminary data from what we have. This is an inlet, and there's a freshwater flow that comes in on occasion. I just wanted to mention that. So do we see low pH conditions in the field? We just got these sondes put out in the end of August, and I could have extended this, but wintertime's still kind of boring, and I'm really excited about next summer, but we don't have those data yet. Okay, so in blue, this is like the bad point, right? If you go below 7.6, and this says in this particular data set there was maybe a couple days that they dropped below that low pH. I have no idea whether that's sufficient to cause weak attachments. So that now tells me, well, I can go back in the lab and ask, is that long enough to make a difference? So what's really interesting is that data I showed you was at the surface at 1 meter. We see something totally different, just 7 meters down, and this is the region where they're growing their mussels. So it's a much lower pH down there. Whoops. So pretty common that they're encountering those conditions. With temperature, do they see high temperature? And here's both the surface and 7 meters. It's colder down below, no surprise there. And it says, well, maybe not, but maybe in the field, just getting to maybe 17 degrees instead of 18 is sufficient to cause them to have weaker attachment. We don't know quite yet. So finally, here's we have more temperature data, so that's why I can show you this. I can't say much about whether pH is causing it. If we had to bet today what's causing all of this, we would put our money in the temperature effect, in part because it's such a strong effect from what we saw in the field. But also when we look at the patterns of attachment at Penn Cove, they have that strong seasonality. They're stronger in the winter and not so strong in the summertime. And it seems to match up pretty well with temperature. So when the water's warm, they're weaker. But I'm still going to say we don't have the chlorophyll data. We don't know much about their spawning season. So I'm still hesitant to put all my eggs in that temperature basket. Okay, so where am I headed for the future? What are we working on? I really take this personally. For 20 years, I've been trying to figure out what triggers these fall-off events. Why do they have leaf attachment? I swear it keeps me up at night. And one of the reasons I want to do this for the aquaculture industry is that if we know what triggers it, then and only then can we start to develop adaptation strategies. We could maybe use these data sondes as an early warning system when we notice that there's a combination of maybe temperature and low food supply. Maybe they should get out and harvest their animals a little bit sooner. That's a good time. Or if it's a matter of the surface waters not being good, they could not stock the animals at that height and start growing them lower. So there's lots of things we could do if we understood the problem. And it's also useful for predictions for future scenarios. We know that the animals now maybe aren't seeing their temperature threshold, but generally people site their farms in places where animals grow well, right? And Penn Cove's kind of special because it's highly productive, there's lots of food in the water, and it's pretty warm. They grow faster. So now fast forward to 100 years or 200 years, it's going to be warmer, and that might mean that that particular site is going to be pushing the animals beyond their threshold, and it's not going to be such a good place. So where can that company go? Maybe the cove 100 miles up the coastline would be good, but that turns out to be Canada. That's not going to be so good for that particular company. And we also know that getting permission from the states to actually have commercial operations can be tricky. So often for these companies, these growers, moving isn't an option.
Try oysters.
I mean, well, yeah, so they could try it, and then they are growing a lot of oysters in Washington State. So one thing that they can do, as I mentioned, Gala provincialis is moving its way up the coast. That turns out that's the Mediterranean mussel. It likes warm water. So one option might be, well, let's switch to this other mussel species. And one thing that might be a hindrance with Gala provincialis is it really hates low salinity. This particular site has a lot of river influence, and so they get these low salinity events, and it might mean that they can't grow either species. Okay, so where am I headed in the future? That's just a map of Washington State, really zoomed in. Here's Seattle, people kind of know about that. And here's the outer coast, and that's Canada. I live up here on San Juan Island. And where we've been working is at Penn Cove on Whidbey Island, and they really are focused on Middle Australis there. Turns out that Penn Cove has another site over here in Filsine Bay, which is warmer, and that's where they grow Middle Scala provincialis, the Mediterranean mussel. So we're now trying to expand our operations to here to see if we can see if there's differences in how these two different species respond to environmental change. I'll say one more thing, why this is so cool. We spent $40,000 to get 2 data sondes at the Penn Cove site. And that was, we're on a secret budget. Yes, we have money, but not lots of money, and that's the best we could do. So we're looking at how do we expand our operations to Filsine. We can send people there, but we don't have another $40,000 to buy 2 more data sondes to see what's happening in the water column. So as part of these projects, we're starting to expand our network. We talk to people in Department of Natural Resources. They think that's a neat project, but they're not really interested in helping us. But it turns out Ian Jeffords, Penn Cove Shellfish, he can get on the phone, talk to the Department of Natural Resources and talk them into why that's such an important site for them to put their resources. So within a couple of days, we went from having no idea how we were going to get these data sondes in to the Department of Natural Resources asking us what we wanted, what they should buy for us. And so they did. They didn't buy the pH sensors, and that turned out to be something we really cared about. And actually, Penn Cove Shellfish bought those because they're the growers and it's really been a fabulous partnership with academia, industry, and government. And I think everybody is winning. Okay, so I want to stop there and have a list of people to thank. Laura Newcomb, Ian Jeffords, who talked about. Carolyn Friedman is also my collaborator. She's really a great shellfish expert that works on oysters a lot, and I've heard. And she's really helped me develop these connections with the shellfish industry and the Department of Natural Resources. So I'd like to stop there and take any questions if I have.
So your temperature effect on the strength of the threads, was that accounting for the animals secreting it at that temperature, or was it just a physical temperature? You collected it maybe when it was strong and then you varied the temperature of the thread.
So we've played around with both of those. When I started, I liked to test my threads always at the same thing, like always 10 degrees and always. It turns out how fast you pull them matters, and so I have my favorite speed, 10 millimeters per minute, just to keep things the same. But it's Laura, because graduate students always challenge what you've been doing. Laura's the one that said, well, why don't you test them at the temperature they were made? So when it was grown at 25 degrees Celsius, that's the temperature we tested it at. But I can tell you, is that what your question is?
Well, I was just wondering if there's a physical effect of temperature on the threads, rather than they're secreting at a certain temperature, which
that's
they
a great
may make a stronger
So
thread.
that's actually where we're headed in currently, and we're going to do less with temperature initially. We're really focused on the pH effect on the plaques, because it turns out a lot of the biochemists for years have been working on mussel adhesives, and we know what mussel foot proteins go into the different parts of the threads. The plaques are not as complicated. And so why is a material different? One is that they could be secreting different proteins. Two, they could be secreting the same proteins, but they are secreted in different amounts. Or three, they're cross-linking in different ways because of the chemistry of the water, or the temperature of the water. So a lot of people say, oh, you got to go and do some genomics or proteomics. And we're doing some proteomics now, but it's pretty difficult work. And I think starting with genomics would be the wrong way to go. What's really cool about the system is one of the few that you have the endpoint phenotype. It's very clear how to interpret the data. We have the glue. And we can say that it's weak or not weak. So that's one of the problems with some of the genomics works that I've seen is they say, well, all this stuff is upregulated, but it's hard to interpret what that actually does to the organism. So this is kind of nice because we have a link to weak attachment that causes mortality. Does that answer your question?
No.
Well, I have actually a full slide for you though. Because what does temperature do? Okay, here is my one idea, and I just want to show you because it's a pretty picture. This is not what normal DISL threads look like. Normally they don't have this little wing here. So this is what happens in high temperature. And my interpretation of this is that they're squirting out the proteins in the mold, but they're not molding very well. So either it's less viscous and it's really runny, because when you want to make an epoxy runnier, you heat it up so that it might be squirting out of the mold, or the animal's tired and can't make the mold very well. But anyway, there's something about those that are malformed, so they tend to be skinnier as well.
Is there any study show that protein might actually be a substrate for bacteria? Because in the summer, things heat up. And if in the boundary layer, pH will go really, really low if bacteria are using it as an organic substrate.
I bet you're right, and nobody's looked at it. And so one of the things I worry about is we have our data sondes measuring
pH over here, but there's some other thing going on in those densely packed animals. So getting understanding what's happening at the micro scale or in the interstices of those muscle aggregations, I think would be really important. So in Rhode Island, let's see, I said they do decay faster. Gretchen did some experiments to see how long do they last different times of the year. It's 8 weeks in the wintertime, and after 2 weeks we can't find them anymore in the summer. So maybe the glue was bad and they popped off, but my other idea is that there's a lot of microbial activity integrated.
How much does the clump size matter, or the geometry of how all the different, because if you have, I mean, if they attach to each other, so if you've got 10 mussels and then the bottom one is hanging on, that's a lot more width, of course. So I just looked at all at how the geometry of those attachments.
So for the early stuff, the biomechanical model, I was worried about that, and to simplify, I made sure it was a monolayer, that all the individuals were attached to the substrate. They were also attached to each other, but that all kind of evens out if they're all a uniform carpet. So I had some conditions under which I made those measurements, but I think it does matter. In especially Middle-East California units, they can be meter high, some of those aggregations. So the ones down at the bottom they're surely not getting any food, and probably don't attach anymore after a while, and this will go to decay, and that's probably what contributes to some of these blowouts. In the mussel farms, they restock the animals 2 or 3 times before they harvest them. So they'll put out the seed in a pretty high density. After a couple months, they take them all off and reseed them at a lower density because they're bigger animals. And they'll do that a couple times. The main concern there is they don't want them to be so densely packed that they don't get enough food. But I think a related issue is that they're so densely packed that they're not attaching well.
On the pH that you were showing, PCO2, you're saying that right now it's about 800. I mean, offshore, that's in the deep upwelling water. Is it because stuff's coming through the strait and you're getting that deep water really close to the island?
Yeah. And I think no one appreciated that 10 years ago. Or even
I'm sure Dick Feely would jump right on that.
That he knew all along?
Oh, no.
I talked to Dick all the time, he wasn't telling me that.
Well, no,
Yeah.
just supposedly I see some close to the shore.
Yeah. So we knew it was offshore, and maybe coming into the canal, but we're quite a ways in. And so I don't think it was appreciated that it was coming that far in. And for sure, we're a marine lab, right? We've been doing marine biology and studying already for over 100 years. And what people say is we've been studying ocean acidification all along. Like all the seawater coming into our seawater tables is really low pH, especially after it's been through all the barnacles that are in the pipes. Yeah, so who measures the pH of their water from their sea tables?